Okay, now let's talk about the concept of relative acid-base strength. So we just saw in that Ka table that some acids are stronger, some acids are weaker. We can actually use that information to predict whether our acid-base reaction is going to be product favored or reactant favored. Okay, so let's think about this idea using Bronsted-Lowry acid-base reaction. Ha plus B minus goes to Hb and A minus. Well, let's first identify the different species that are present. We have our acid, and then we have its conjugate base, and then we have our base and its conjugate acid. If we look at the two acids, the HA, the acid itself, and the conjugate acid of the base, HB, if HA is a stronger acid than HB, if one has a larger K than the other one, then by definition, HA will release more proton compared to HB, okay? And that means the A minus is not able to keep that proton along, so it's more weakly bonded to H plus compared to B minus. If that's the case, then A minus is a weaker base because the function of A minus is to attract protons. So if it's not doing as good a job as B minus, then it's a weaker base compared to B minus. So now we just deduce, just by thinking about it, that if HA is a stronger acid than HB, then automatically B minus is a stronger base than A minus. Okay, so here we're talking about acid, here we're talking about base. If you look at HA and B minus, they're both on the left side. So that means we have the stronger pair on the left side, right? So we have a stronger acid. Again, not strong necessarily, but just stronger, okay? Then B minus is the stronger base. HB is the weaker acid. A minus is the weaker base. So if you have stronger, then of course there's more reaction going on because one thing really wants to give away its proton, the other thing really wants to pull that proton away. So there's a lot of reaction going on the left side compared to the right side where the weaker acid doesn't really want to give the proton away, whereas the weaker base also doesn't really want to pull that proton away. So this reaction would then be product favored. Go towards the right side, the product side. And again, because there's just more reaction between the reactants to form product, the product doesn't really have that much tendency to react with each other. If the reaction is product favored, then the K of the entire reaction is going to be much larger than 1, just like we learned in the equilibrium chapter. Notice I'm not saying the Ka, I'm just saying the K, okay, the K of this reaction. Ka is a very special equilibrium constant. It is specific to a reaction where an acid reacts with water, okay, so it's this reaction right here. K value of that is called Ka, but when we just write a generic base like B minus in our equation here, then we just call the equilibrium constant K. We don't call it Ka. Okay, so now you should be able to rationalize to yourself, same thing, if HB is stronger than HA. So we just flipped the beginning assumption. Earlier we said HA is greater than HB. Now HB is a stronger acid. Go through the same reasoning. HB will produce more proton. Therefore, B minus is not as good at keeping the proton, so it must be a weaker base compared to A minus. Therefore, now, if we look at the reaction, again, same reaction, we have the weaker pairs on the left side, okay? So the weaker acid, this is the stronger acid, and then this is also the weaker base, and this is the stronger base. So, stronger on the right side, therefore, it's going to be a reactant favored reaction. K must be much less than 1. What this is telling you is that the acid strength is inversely proportional to the conjugate base strength. The stronger an acid, the weaker its conjugate base. Okay, that should make sense to you because the stronger the acid, the more likely it is to give away its proton, which means its conjugate base is not very good at keeping that proton. Therefore, it's a weak base. Okay, vice versa. If you have a weak acid, its conjugate base is stronger. So that's really how you interpret this table. Remember that the acid strength goes lower as you go down until you get to water, which is the weakest acid that could be present in an aqueous solution. OH minus, on the other hand, is the strongest base that you can have in water. Okay, as you go up, the base gets weaker and weaker as the acid gets stronger and stronger. So once you get to the point where you hit water, that's the weakest base that could be present. Anything above that actually is no longer a base. We don't call these guys bases. They're just ions at that point. They don't do anything in terms of acid-base reaction because water, which is always present in this aqueous solution, will take over as base. So if I'm an acid and has a choice to react with either chloride or water, I'm always going to choose to react with water. Why? Because water is a stronger base. You're not going to react with the weaker species. The stronger one is going to be the one that is going to pull the proton off and do the base function as opposed to Cl minus. Okay, so hopefully that makes sense. Take a look at an example here just to get us an idea of how to use that Ka table along with the concept we just learned about relative acid-base strength. So we have HNO2 plus Cn minus forming HCN and NO2 minus. And we want to know what's the direction of the reaction. Is it product side or is it reactant side? So again, the first step is just to compare the strength of the two acids. So we need to label our acids first. This is an acid. This is its conjugate base. So the second acid is this one, and that's the base. This is actually the conjugate, right? And so you're comparing the two acids, HNO2 and HCN, and see what the strength of those two are. So you go to the Ka value, and looking at the HNO2, we see that right here. That's the Ka value, about 10 to the minus 4. And then we look at HCN, which is right here, and its Ka value is 10 to the minus 10. So HNO2 is a stronger acid than HCN based on Ka value. So automatically, this is the stronger acid. Now, as soon as you figure out that's a stronger one and this is the weaker one, it's automatic that the base here, Cn minus, is going to be the stronger base, and then the NO2 minus will be the weaker base as well. So again, as soon as you know the relative strength of the acid, you will automatically know the relative strength of the base. Because the stronger pair is on the left side, this reaction is product favored. I want to summarize some of the things we just talked about, the relative acid-base strength, as well as how acids and bases behave in the presence of water. I want to remind you that we're always talking about aqueous solution, whether it's an acid or a base, are dissolved in water, and water itself has the ability to act as an acid or a base, so that's why its role has to be explicitly discussed. So the first conclusion we have is that if an acid is strong, so not stronger, but strong, that means that it dissociates completely in water. By equilibrium, all the acid disappears, all you have is proton in the conjugate base. If an acid is strong, its conjugate base has no strength. In other words, it doesn't act as a base. And this is because its conjugate base would be an anion that is weaker than water as a base. Okay, so again, I'm going to bring this table up here to show you what I mean by that. And what you need to remember is that the acid here gets stronger as you go up, the base gets weaker, right? Because remember, there's that inverse relationship between acid and conjugate base strength. So water is here as a base. So these ions right here over on the top, okay, all of these guys, they are weaker than water as a base. So therefore, if I'm an acid, there's no reason for me to react with them when water is available, because water is going to take over and pull the proton off the acid as opposed to any of these guys. So that's the first conclusion. None of these ions are basic. In fact, when we talk about how to determine acidity later on, we would say that these are what we call our neutral ions. Now, everything below water, though, all of these guys down here, these are basic. So these are actually important. They're basic ions. So if I have water versus one of those guys, I'd pick one of those guys. They're stronger than water as a base. Now let's take a look at the second conclusion. H3O plus is the strongest acid that can exist in aqueous solution. You can have stronger acid, but as soon as you place them in water, water is going to convert them into H3O plus. So H3O plus is right here. All of these guys here at the top are stronger acids, but when you put them in water, what water will do is automatically pull the proton and convert them to H3O plus. So none of those species can exist in water. You will never see HCl exist as HCl in water. It will appear as H3O plus and Cl minus. If you have weaker acids than H3O plus, then they will stay together. So for example, all of the guys down here, around here, okay, anybody lower than this, they're weaker acids than H3O plus. So when you mix them with water, yes, part of it is going to get converted to H3O plus, but the majority of that acid actually stays as the molecule itself. So HF would stay mostly as HF when you mix them with water. HCl, on the other hand, will not. It will break apart and become H3O plus and Cl minus. That's something that's really important to understand. Strong acids completely break apart, weak acids stay together. This concept about the fact that acid can't get any stronger than HCl plus is what we call a leveling effect. It just means that as soon as anybody stronger comes in, it's going to get leveled down to the strength of H3O plus. So how do we know then that HI is stronger than HCl if they all have the same strength in water? Because they all become H3O plus. The key is not to measure it in water. So you can actually measure the strength of acids in some other solvent. In fact, you want a base that's weaker than water, and that would be able to tell you which acid is going to preferentially react with that base. One of the things that we can do is measure the strength of the acid. For example, in ethanol, which is a weaker base than water. So if you use ethanol, you'll be able to tell that one of these acids is going to react more with ethanol compared to the other one. And that's how you tell that, in this case, HI is stronger than HCl. The last conclusion we want to draw is about the base side of that table, which is the OH minus. So OH minus is the strongest base that can exist. So again, looking back now on the right side, which is the base side, you notice that OH minus down here, remember that that's the strongest base possible, because as you go down, the base gets stronger and stronger. You don't go below that, nothing exists. Yes, you could put bases that are stronger than OH minus, but as soon as you mix them with water, it's gonna convert itself to OH minus, just the same way as if you put any stronger acid in water, it will convert itself to H3O plus. And similar to the acid concept, if you have weaker base than OH minus, it will stay there together and a small part of it will get converted to OH minus. So for example, if you have, say, CN minus, right, which is weaker as a base compared to OH minus, it will react with water to form OH minus, but a majority of it will stay as CN minus.